Thank you. So this would be on the theoretical end of the spectrum compared to what we've heard so far, sequence design problems. But let me, before I start with the main topic, just mention briefly a paper that just came out in Genome Research, where we analyzed the methylation patterns of thousands of tumors, 25 cancer types, and enhancers seem to be the most differential in terms of the methylation pattern that they show between the normal and the cancer tissues, and this is pretty uniform across the tissues. These methylation patterns distinguish very nicely the primary tumor types according to organ and source. And specifically regarding metastasis, we found particular enhancers whose methylation is correlated with survival, and some of these were new and were tested experimentally. And now to the main show. So we are talking about transcription regulation, both on the DNA and the RNA level. So TFs regulate gene expression, and RNA binding protein regulate post-transcription run regulation. And the way to measure these is on the TF level is using protein binding microarrays, or what we've heard from Nadav, the synthetic enhancers that one inserts into the living animal. And in both cases, if we want to probe systematically the set of possible targets, we need to design a set of double-stranded sequences that together cover all the k-mers, and this was actually done in both cases. Similarly, when measuring protein RNA binding, one RNAcompete, for example, covers all possible 9-mers multiple times in unstructured RNA probes, namely those that don't form secondary structures. And again, to probe this, to evaluate this set of probes requires coverage of all RNA k-mers. So here, of course, the problem is single-stranded. Now, the tool that we are using are the Bruijn sequences. So just a reminder of the definition. The Bruijn sequence of order k over alphabet sigma is a sequence where each k-mer appears exactly once. And this is, of course, the most compact representation, and the length will be size of the alphabet to the power of k. And it's a very well-established field, especially now that it's also become highly popular in next-generation sequence analysis. And one of the ways to generate such sequences is using linear feedback shift registers. Now, such a design was actually used for the original PBM, but it is there are some improvements that one can do over the basic use of the Bruijn sequence. And this is the fact that we are talking about, in the DNA case, we are talking about double-stranded DNA. So whenever we design the blue sequence to cover all k-mers, we are in fact also covering all these k-mers using the other strand. So any k-mer that we generate on the blue sequence gives us for free the green segment in the reverse complement. So one would think that a better design would be, a more compact design would be possible. And similarly, in the RNA case, we want to avoid the structured RNA probes because they are not useful to us, and we would like to create a subset that will be more efficient. So the first challenge is how to cover all DNA k-mers in double-stranded probes. So you use the reverse complementarity to save. And let's define a sequence to be reverse complementary de Bruijn if it covers all k-mers either in the original sequence or its reverse complement. Namely, each k-mer either is contained in K or its reverse complement is contained in K. And our goal now, the new goal, is to generate a minimum length reverse complementary de Bruijn sequence. And the algorithm that we developed is actually an extension or generalization of the Euler tool, which is used to generate the classical de Bruijn sequence. So what we do is in the Euler tool algorithm, one continuously moves along a path, looking always for a new edge out from the current node. And what we'll do is to build both the sequence and its reverse complement at the same time. So while traversing an edge, we mark both that edge and its reverse complement edge. So here is a tiny example. We start from this node, and here is the reverse complement, and we move to the next, and then we move to the next, etc. So if we can fulfill this process, then we have actually at the end of the day, we will have two cycles, one reverse complement to each other, and each them will be half the size of the total sequence and will provide us a solution. And in fact, the running time of this is optimal. So this works like a charm for odd k, because one could prove that the algorithm works under three conditions. First of all, the graph must be strongly connected. Then every vertex must be balanced, same in degree as out degree. And in addition, so these are the conditions from the classical Euler tool, and we have an additional condition that has to do with the reverse complementarity, that there should be a pairing of edges into reverse complementary pairs. And the problem starts when we are looking at the case of K even, and then they will have palindromic edges. So whenever we use these edges in the green path, it's already used, so we cannot reuse it in the red complementary path. So this is the problem. And the simple solution is just to add cycles. So for example, here is one palindromic edge, and here it's reverse complement. And we add a cycle to our graph containing these two palindromic edges and the edges that will connect them together. So we look at all the cyclic shifts. So here we take care of two palindromic edges, and the result of our process is that we'll have both pairing. So these two edges it's a palindrome, so it's a reverse complement of itself. Same for here. And these two edges in the path, the cyclic shifts will also be reverse complement. So we preserve the degree constraints because we added cycles, and we preserve the pairing condition, and of course stronger connectivity is remaining from the original problem. So we satisfy the condition of the theorem, and now we can apply the simple RC Euler 2 algorithm and solve the problem on it. Okay? So we already said we preserve connectivity and balance, and we can show, it's a simple lemma to show that actually the cyclic shifts are also fall into a collection of pairs.
Just so that I understand, so the cycle was already there in the graph, but now you sort of...
I doubled it. No, I doubled it in order to have two edges here, so that I will be able, when I move on this edge, to move also on the reverse complement, which is the same edge. So I created a parallel edge here in order to have the possibility to create these two cycles simultaneously. And if I just added these edges, I will destroy the balance, and therefore I add the whole cycle. Now this is actually boils down to a very simple algorithm. We augment the graph by the cycles, and then we run the RC Euler algorithm. And this takes linear time, but it doesn't guarantee optimality. So the sequence lengths will be slightly more than optimal. And in fact, I'll not show here, but we developed a network flow formulation that gives us the optimal sequence lengths at time that is the network flow type complexity, so low polynomial. We can also show a simple lower bound for the length of the sequence for order k. This is the optimal case where k is odd. When k is even, we have a lower bound that depends on the number of palindromes. And so the interesting cases are just for k even, so we plot them here. Here you see just using the original De Bruijn sequence algorithm. This is the lower bound that the theorem gives. This is the linear time algorithm by adding the cycles, and this is the results of the optimal algorithm for network flow. And you see that the difference begins to show at size 10. The difference is tiny. So in terms of practical reasons, one might as well use the linear algorithm. And indeed, we have a saving factor of approaching 2. So we need half as many sequences as the original problem. And now Yaron will do the rest.
Okay, so I'm going to present a solution to the second challenge, that is to cover all k-mers in unstructured RNA probes, and this was done together with Professor Berger from MIT. So first I'll give a formal definition of the problem, and the problem is defined based on 3 parameters. One is the k, the value that you want to cover. L is the length of the probe on the microarray, and p is the number of times you want each k-mer to appear. And we define a p multi-k-mer coverage as a set of sequences that together cover all RNA k-mers, and each k-mer can appear exactly or at least p times, depending on what we want to cover. And the goal is to find the minimum p multi-k-mer coverage by a restricted set of L long sequences. So this is the general definition of the problem, and the application that we want to solve is the case where the restricted set is the set of unstructured RNA probes. So it turns out that this problem is NP-hard, and before I go and show the proof or an overview of the proof, I'll just mention that it is an easy...
Sorry. What is the mathematical definition of unstructured RNA?
Okay, that's a good question. Actually, I left the slide out, but we followed a definition that was given by the developers of the RNAcompete technology. And what they did there, they ran RNA shapes. It's one of the algorithms to predict RNA secondary structure. And what it gives is an ensemble of representative structures. And for each one of the structure, it gives a free energy estimates as well as a probability. And then they look at all of the structure that are below a certain threshold of free energy, and they sum the probabilities. If the sum of the probabilities is higher than half, they consider the probe to be structured. Otherwise, it is unstructured. So this is the definition that we followed from the technology, from the people who developed the technology.
List of sequences as output from this thing, and you want to, under that constraint, you want to solve this problem.
So I want to cover all k-mers in unstructured sequences, I guess. I mean, here it's the same sequence, but you can predict different structures for it.
But I can think just that you have an oracle which returns whether or not a sequence is structured.
Yeah, so that's okay. Yeah, that's what we apply. That's what we assume here. Yeah, I mean, we have this script that gives us a binary value, 0 or 1. Yeah, exactly. So that fits the formal definition of the general problem. So first, so I just want to mention that it is an easy problem when we allow all L-long sequences, and then we can just take the Bruijn sequence and cut it into pieces, or in the case where L equals K, and then each sequence is a k-mer, so we would like to have all sequences. Now, you might have already sensed a flavor of this problem, which is similar to the well-known set cover problem. And here we are going to reduce from a variant of the set cover problem, which is the minimum M set cover. So each set can contain at most M elements. And the goal is to find the smallest subset S prime of these M sets that together cover all the elements. And here is an illustration of that problem. So we have a universe, in this case, of 10 elements. And we want to find the subset of this set that together cover all elements. In this case, there is only one solution because each set contains a unique element, but this is just an illustration. And the analog is going to be that each element is going to be a k-mer, and each sequence is going to be a set that contains these k-mers. But these problems are not equivalent, and the reduction is not immediate. And the main difference relies in the membership of elements that is independent in the case of the set cover problem. So if I have element EI, I can have element EJ without any consideration. The membership is independent. But on the other end, when I have a k-mer ACGU, for example, I am guaranteed to have the k-mer CGU and some other nucleotide. So there is a dependency between the k-mers that are members of the same sequence that comes just from the overlap of k-mers. So we need to use some trick to solve this, to resolve this dependency. And here I give an overview of the reduction. So first, we take each element and we map it to something we call an A representation. So we choose K to be the ceiling of log of the number of elements to the base of 2. So we can represent each element by a binary vector. Then we can turn each element by its number to a binary representation, and then just convert the bits to A and U. So we have this A representation. Now we want to put all those representations together, but we don't concatenate them as they are. We prepend each representation by KGs and append by KCs. And in that way, we can break the dependency. So we need this set of sequences to cover all of the original elements, and we will have other sequences that will be able to cover all the G and C k-mers that we have in the set. So we need to augment this set with additional sequences, which I am not going to mention here because it's a technical detail of the reduction. But basically, this is the set of sequences that corresponds to each of the original sets in the input to the set cover problem. Then we can just give the set of sequences and find the k-mer coverage over the alphabet ACGU. And luckily, the running time of the reduction is polynomial, so it is safe to say that the k-mer coverage problem is NP-hard. So we got something bad from being similar to the set cover problem. Maybe we can benefit from that as well. And there is a well-known greedy algorithm that has a guaranteed approximation ratio for the set cover problem, and that the approximation ratio is logarithmic. It's in fact the harmonic sum. So we can use it in our case as well. We can apply the greedy algorithm and get this ratio of the harmonic sum, which is a sum from 1 to the size of the maximum set in our input. And in our case, all of the sequences contain the same number of k-mers, so it's an harmonic sum up to L minus k plus 1. And the harmonic sum is bounded by the natural log plus 1. So this is going to be the first algorithm. We first have to find all L-long unstructured RNA sequences, and once we have those, we can apply the greedy set cover algorithm, where the elements are going to be all RNA k-mers, and the sets are the unstructured sequences. Unfortunately, the running time of either of these steps is at least 4 to the L, and L is 35 or greater in most of the application that we saw in the introduction, so this becomes an impractical algorithm. So this leads us to developing a heuristic algorithm, which actually does not, disappointingly has no guarantees, but works well in practice. And the key point is that we are going to find these random walks in the Bruijn graphs that together cover all of the edges. And these random walks have to represent unstructured sequences. And in addition, we have to come up with some backtracking strategy, because it might be that we find a path but it is structured, and we find another path that is structured, then we have to have a few attempts till we find the unstructured path. So these are the key points that we need to take care of in our algorithm. So this is the second algorithm that I'm going to present. And we start with generating a De Bruijn graph of order k-1. So this gives us that each edge represents a k-mer. And then we can also add copies in case we want a multiplicity that is greater than 1 for each k-mer. Then we iterate as long as there are still edges in the graph, because it means that there are k-mers that we didn't cover. And we try to find an unstructured L-long path. If we find one, we can output and remove the edges from the graph. And if we did not find, we can keep trying till some number of attempts. It can be set by the user. And if we did not find, we try to look for a path that is shorter by 1 nucleotide. And we keep on going, and we might be shortening the path a lot if it's very difficult to find an unstructured sequence. And if we get to a length of k-1, this means that we find an empty path, which has no meaning. So we just output a random edge from the current vertex, and we move on to looking for a new path. In case we closed a cycle, which can also happen, we just output it, and we continue from a new visited vertex similar to the Euler 2 algorithm. So in the end, the running time that we get is proportional to the number of probes times the running time of the secondary structure prediction algorithm, which is usually bounded by the length of the sequence, L square, where L is the length of the sequence, times L, because this is the number of extension or shortenings that we might do for each probe. The number of probes is in the order of 4 to the k. Now, the output of this algorithm is going to be a set of sequences that together cover all k-mers, and each k-mer appears exactly p times. But it might be that not all of these sequences are of the same length L. And it might be a requirement of the technology that all of the oligos on the microarray have the same length. So we suggest another heuristic algorithm to extend all of the oligos to the same length. And the cases that we have shorter oligos are when we closed cycles or we found structured k-mers. This is this, yeah.
You simply avoid cycles by marking all the places you've been and simply excluding the random walk from stepping to those
Yeah,
points?
that's another possibility. But then you might have been left with just paths that are shorter because you didn't go into these paths. These edges would be in the graph. You need to cover them in some way. So it might be that you are left with a short path just to close this cycle because you didn't want to cover it. And one of the requirements is to cover all k-mers. So one way or the other, you would need to go over these edges and include them in some path, and the path might be shorter than L. So first we just try a random extension. So we place the short sequence in some random position in the oligo and assign random nucleotides. If we succeed, we can output it. Otherwise, if we fail, we suggest that we break these sequences into two equal-sized pieces, overlapping, so we don't lose any k-mer, and then we continue recursively. If eventually in the recursion we got to a size of k, then we have nothing more to do, but we output the k-mer with some random nucleotides. So some notes about the implementation details. So as I've already noted, we limit the number of random attempts that we do in the algorithm. Yeah.
Just for an understanding, what fraction of length L probes are unstructured?
So I have that as a hidden slide. And so, for example, for the length of 45, it's less than 10% of the probes. For length of 35, it's about 20%. So these are the values. Yeah. So that's why just using a random De Bruijn sequence doesn't work, because most of these will be structured. Yeah. Good question. So we limit the number of random attempts. Otherwise, if we do an exhaustive search, it might take 4 to the L. We do some improvement in the running time in the extension by doubling the probe length. So we go from a factor of L to log L. And we also can get some improvement, but it is not implemented, by doing the extension and using already solved sub-problems of the secondary structure prediction algorithms, which usually work in using dynamic programming. So I'll go on because I'm short in time. So now going into the results, and the question was, what can we compare to? We don't have an optimal solution. So first we suggest to compare to a theoretical lower bound, which is only based on the number of k-mers that need to be covered, and this is 4 to the k times p, divided by the number of k-mers we can fit in each sequence. And we also suggest a naive algorithm which generates random oligos if it is an unstructured oligo that covers uncovered k-mers, we add it to the pool. And here are the results. So we ran the algorithms for length 30, 35, and 40, and for different values of k. And first, looking at the incomplete set. By incomplete, I mean that some of the oligos may be shorter than L. We see that the ratio compared to the theoretical lower bound is about 1.1. So not too bad. We are not increasing the size of the set too much compared to the theoretical lower bound. When we are looking at the complete set ratio, where all oligos are of length L, we see that already we get some ratios between 1.1 and 1.3. Now, looking at the naive set that is generated by the naive algorithm, it is doing much worse. It produces a library that is about 4 or 5 times greater in size than what we produce. And I should also note that, as you see, starting from k equals 9, we also get some structured probes in our pool. And the reason for that is that there are some self-structured k-mers. So these are k-mers that form structure with themselves. So we have no way to include them, but to include some structured probes. Another way to define the problem would be to exclude those and then cover all the rest of the k-mers just with unstructured probes. Now, we also compared the specific design of the RNAcompete technology, and which was the way they did it. They took the Bruijn sequence generated from linear feedback shift register and then used some ad hoc rules to generate a library of the properties that they wanted. So in our case, we just ran the algorithm with k equals 9, length for 35 for the probes, and the multiplicity of 16. And what we see that the ratio that we get is 1.07 compared to the theoretical lower bound, compared to the library they used, where the ratio is 1.38. So that is a huge reduction in the number of probes needed to cover all k-mers in unstructured sequences. In addition, the number of structured probes that we included in the set is also smaller, 3 times smaller than what they used. And just to add to that, in our design, all of the oligos were of the same length, 35. In their design, they had variable length, 35 to 38. It might be that if we were allowing our algorithm to use different lengths, we can also have reduced the size of the output of the result. So some future extensions, we hope to generalize to other properties required for DNA or RNA probes. We know that it's a very flexible scheme. So if, for example, we want to remove some k-mers or to exclude them, we can just remove the edge from the graph and rerun the algorithm. And indeed, in the RNAcompete technology, for example, 2 k-mers were excluded because they were cleaving sites of the enzyme that was used in the protocol. We can also assign different multiplicities to the different k-mers and just rerun the algorithm. So to summarize, I hope that in this talk I convinced you that the Bruijn graphs are very useful for the purpose of designing libraries of RNA and DNA probes. I think one of the reasons why they are so useful, because they are much more flexible, and indeed they can produce all possible de Bruijn sequence. Any de Bruijn sequence can be as a corresponding Euler-Turing algorithm in the graph, in the de Bruijn graph, as opposed to linear feedback shift registers, which have a much more limited number of de Bruijn sequences it can generate, which is the number of primitive polynomials over a finite field. And we hope that with this new algorithm, we can design more libraries depending on, and you can just plug in a difference property, some script that produces 0 or 1 and rerun the algorithm on that. So thanks to the labs from which these 2 works came from. The first DNA work was when I was a PhD with Professor Shamir, and the second work is with Professor Berger doing my ongoing postdoc. And thanks for your attention.
Time for a couple questions?
So you choose start point randomly, right? Edge also randomly. And have you tried to choose multiple starting points and run the same thing and compare is there any consequences?
No, so I didn't go into this direction. I guess choosing a few random points, you would maybe they would collide or something like that. So you would have to resolve another issue in the algorithm.
I'm still curious about the definition of unstructured, or the times at which it's computed. Presumably you don't pre-compute for each port of the Elmer whether it's structured or unstructured, right?
No, it is part of the algorithm. Every time it does an extension, it runs the...
Okay, so you do it as you walk across a step, you consider the new Elmer that would be formed from that traversal.
Yeah.
Okay, that makes more sense.
It's not pre-computed for all possible elements.
Right.
Yeah.
So would your algorithms be applicable to all these capture probe design, say, for example, for like all the repeat sequences in the genome and so on?
Well, I think it depends if they need to cover all k-mers or a subset of the k-mers, but if they are looking to include genomic sequences, then it's not as applicable.
You know, if I want to capture all the repeated regions, a sub-collection of regions in the genome, and I'm trying to design a set of probes that, you know, a small set that will cover them.
Yeah. If they can represent it by a subset of k-mers, and then these k-mers are edges in the graph, then you can run the algorithm and find paths that cover all of these set of k-mers. Yeah. So theoretically, it can be applied.
One more quick question.
Yeah, so since your algorithm is random, I suppose the results also are random.
Yeah.
So, can you say what about the variability you observe in the results?
I didn't check that. Yeah. I mean, for the small numbers, it's just an impression. I mean, I don't have systematic proof. I saw that I get about the same numbers because I think the number also. I mean, that's just an impression. So I don't have systematic. Number are so big that the variance would be small, but yeah, I don't have a systematic evaluation of that.
So this universe is one run? Is that?
Yeah, it is produced by one run. Yeah.
Okay, well, let's thank both speakers again.